Um, Hi, my name is Amerson, and today I will be presenting my math project about finding a feasible region through question 498. So, just to begin, I'll be explaining question 498 and using it as an example on how to find feasible region. To begin, I'll read out the question. Mackenzie could spend at most 2 hours on math and biology homework tonight. Biology reading always takes at least 45 minutes, but because there's also a math hand due tomorrow, Mackenzie knows that math is going to require more time than biology. From the question, I created 3 statements. That math and biology takes up at most 120 minutes, which is equal to 2 hours. Biology takes up at least 45 minutes, and math takes up more time than biology. So, moving on to part 1 of the question, using the variables m and b, express the constraints on Mackenzie's study time by a system of inequalities. Work in minutes. So, on part A, I substituted m for math and b for biology, and used my aforementioned statements to create these inequalities, with m plus b being less than or equal to 120, b equal to or more than 45, and m is more than b. So those were the inequalities that I used for the rest of the problem. On to part 2 of the question. Graph the inequalities with m on the horizontal axis and b on the vertical axis, and highlight the region that satisfies all 3 inequalities. Such a region is called a feasible region because every point in the region is a possible feasible solution to the system. So this is the point where they actually begin to talk about feasible region, and to go on more about it. Feasible region happens when you have a system of inequalities, and these inequalities, when graphed, display a region that overlaps with all of the inequalities and provide a solution to all of them, or that satisfies all of the equations. So, to begin, I changed the variable m to x, and the variable b to y, and made the first equation or inequality easier to look at or easier to graph by making it into mx plus b form, or slope-intercept form. So as you can see, this is my graph right here, and I graphed it all out. So this is the first inequality, the second, and the third, and these lines are this is the region of each line individually, with arrows coming out from the bottom or the top, for that matter. So from these equations, you could tell the direction of the regions of each line. I'm going to actually go into Desmos now to display this better, right? So to begin, right, this is the same graph, except more accurately displayed because it's on a computer. But just to highlight how this works, right? So we have the line y is equal to 120 minus x, right here, and then because it's an inequality, it's being shaded downward because it's a y is less than inequality, so it would have to be below the line. So below, not above, because it's less than. So the y is gonna be smaller and smaller and smaller, but it's also infinite because it's a line. But on the other hand, we have y is greater than 45. So we have the line y is greater than 45 right here. But then we also have it shaded upward because it's a greater than sign, and y is greater than 45. So the y just keeps on increasing and increasing and increasing. And also we have all the x's. But also we have our last equation, x is greater than y. But the thing special with this one is that because it's only a greater than sign and not a greater and equal to sign, it's a dotted line because none of the points on the line are actually possibilities, because compared to y is greater than 45, um, the points on the axis of y equals 45, those are included. Anyway, to further on onto feasible region. The feasible region is the point where all of the graphs overlap, with all of their shading overlapping as well. So on our graph we have here, this is the feasible region, because this is where they all overlap. And to further that sentiment, we're also going to have a test point with part C of the question. Is the point 60, 50 in the feasible region? So there's two ways of going about this, right? We go back to the graph. Let's use Desmos, actually. We go back to the graph and then find 60, 50, which is very easy, because this is 60. Then 50 should be right here. So, yeah, okay, it is in the feasible region. But let's say in another case that we don't have such a beautiful algorithmically correct computer graph, or Desmos for that matter. We would have to do this algebraically. So, remembering what they said in part B, such a region, that highlights the region that satisfies all three equations, right? Inequalities. That means we have to test if the points work in all of the inequalities, right? So to do this, all I did was plug in the points for the x and y. So from what I pulled out, they all worked out. So I said yes, it is, because it satisfies all equations. And yeah, that's kind of it. But the main takeaways are finding feasible region, which was used by graphing out each of the inequalities and then finding where it overlaps, and test point, which was plugging in a point into the equations and seeing if it was correct or not. And if it's not in the feasible region. But if it is in the feasible region, that is. And creating those system of inequalities. But beside that, that's really it. Thank you. Good night.